Section 2.2, Algebraic Functions. In this section, we will review common functions including polynomial, rational, power, and root functions. We will also graph piecewise-defined functions. We begin with polynomial functions. In an earlier lesson, we reviewed function notation, domain, and range of functions, and we talked about one particular type of function called linear functions, which is just simply a first-degree polynomial function. In this particular section, we will begin by looking at polynomials in general. So what exactly is a polynomial? A polynomial is a math quantity that includes the sum or difference of multiple terms with x's in them, or just constants, or the product of x's and constants. So something like 3 plus 2x squared minus 4x cubed is known as a polynomial. Something like 5t to the power of 5 minus 2t cubed plus 7t is another example of a polynomial. Now, each one of these individual items that make up a polynomial is known as the term. So terms begin and end when there's a plus or a minus. So for example, 3 is one term, 2x squared is another term, and negative 4x cubed is another term. The highest power that you can find in the problem is known as the degree of the polynomial. So for example, in this case, the 3 plus 2x squared minus 4x cubed, the highest power that we can find is 3. That's the power of a variable, so therefore it's known as the degree of the polynomial. And the leading term is the term that has the highest power. So in this case, that would be the negative 4x cubed. And the leading coefficient will be known as negative 4. Even though it's written at the end, we will call it the leading coefficient. Now, there are different types of polynomials. There's special polynomials called binomials or trinomials. Those are made up of 2 terms or 3 terms. And also there's monomials, which are polynomial made up of only 1 term. So in example 1, we are given some polynomials and we're expected to identify the degree, the leading term, and the leading coefficient. So the first thing we're going to do for all of these is write them in standard form. So what exactly is standard form? Standard form is when you write the polynomial in descending order from the highest power down. So you're going to look at each one of these polynomials, the 3 plus 2x squared minus 4x cubed, for instance, and you're going to start by writing the polynomial in standard form, meaning the highest power goes first, then the next highest power, and so on until we get to the constant term. So let's go through all these polynomials and write them all in standard form. So the first one, by reading it, we will need to put the negative 4x cubed first, then the 2x squared next, and finally the 3. For the next one, 5t to the power 5 minus 2t cubed plus 7t, it is already in standard form, so I'm just going to copy it as is without making any changes whatsoever. The third one has 6 to the power 5p minus p cubed minus 2. So the p with the highest power is the negative p cubed. That will go first. And then we write everything else in descending order. So next we will have to put the 6, 5 to the power, and then times p minus 2. So in this case, it doesn't matter that the 6 has power 5. What matters is the variables and their power. So the p here has power 1. That's why it goes after the 3. And finally, the last one, 4x squared minus x to the power of 6 plus 2x minus 6. The x to the power of 6 needs to go first. Then the 4x squared, and obviously it's positive. Then the 2x, then the negative 6. So now that we have identified the standard form of each of these polynomials, we're going to identify the degree of all of these polynomials, and I'm just going to highlight it in blue. So the degree of the polynomials is the highest power we can find in the polynomial on any variable. So for the first one, the highest power we can find is 3. For the second one, the highest power we can find is 5. For the next one, there's 2 powers that we can see, the 3 and the 5, but the 5 is the power of 6, so that doesn't count. So we just decide that the power that we can find is 3. And finally, the last one, the highest power is 6. Those are known as the degree of the polynomials. So next, let's decide the leading term. The leading term is the term that has the highest power. In the first case, it's negative 4x cubed. In the second case, it's 5t to the power 5. Then negative p to the power of 3. And finally, negative x to the power of 6. Finally, we want to decide what the leading coefficient is, and the leading coefficient is the number inside of your leading term. So in this first case, it's going to be negative 4. The next one will be 5. The next one has a negative p to the power of 3 in the leading term. So therefore, the leading coefficient will be the negative invisible 1. And finally, the same thing applies on the last problem. There's an invisible negative 1 next to the x to the power of 6. Those are the leading coefficients. Okay, so an important characteristic of the graph of a polynomial is where it intersects the x-axis. This is the place known as the x-intercept, or the root, or the zero of the function. So all these words are interchangeable. The root, the zero of the function, or the x-intercept are all the same. In order to find the place where the function crosses the x-axis, you'll need to set the equation equal to 0. And then you find the x value that allows the function to become 0, to give you the output of 0. Now, sometimes when you're doing this, you'll need to factor. Sometimes you'll need to use the quadratic formula. So it depends on the problem, and it depends on the polynomial that you're given. But it's a helpful property to know, this zero product property, which says if a product of two things, a times b, is equal to 0, then either the a had to be 0 or the b had to be 0. This is some property that we will use sometimes when we factor and we want to find the zeros of a function. So let's demonstrate by doing example number 2. It says find the zeros of the function y equal to 2x squared minus 5x minus 3 by factoring the problem, then using the zero product property. So in order to find the zero of the function, or the x-intercept, or the place where the function crosses the x-axis, we're going to let y be equal to 0. So in other terms, we're going to take the 2x squared minus 5x minus 3, and we're going to set it equal to 0, replacing the value y with 0 itself. So once we do that, we will have to factor this problem, and I'm going to revert back to the thing we learned before, which is this big X method, also known as the sum product method. Let's grab the 2, let's grab the negative 3, and multiply them. That's going to give us negative 6. And we will grab the negative 5 from the middle and put it on the bottom of the diagram. Once we do that, we have to ask ourselves the following question. Can we find two numbers that multiply to negative 6, and when you add them, you get negative 5? So think about that for a second. Two numbers that multiply to negative 6, and when you add them, you get negative 5. Well, I'm thinking negative 6 and positive 1. When you multiply those two numbers, you get negative 6, and when you add them, you get negative 5. And because we have 2 in front, we will start by rewriting the problem as 2x squared. Then we will plug in the negative 6x, then the 1x, finally the negative 3. And we have to go through the process of grouping. So the first group, 2x squared minus 6x, what do they have in common? The second group, the 1x minus 3, what do they have in common? Factor out the GCF and keep factoring. So 2x squared minus 6x, we can factor 2x out, and when we do that, we get x minus 3 left over. And although the second couple, 1x and minus 3, have nothing in common, we can always factor the 1 out. That gives us x minus 3 inside the parentheses. Now, as you can see, we have the x minus 3 repeating in the first term and in the second term. So therefore, we will factor the x minus 3 out and dump everything else into the second set of parentheses, which is the 2x plus 1. And obviously, there's nothing between these parentheses. That means it's multiplication, even though it's not written. We understand it's there. And this is where that zero product property is going to be helpful. We have a product of two parentheses, and it equals 0. So according to the zero product property, I'm going to be referring to it as the ZPP. Either the x minus 3 has to be 0, or the second factor to 2x plus 1 has to be 0. And solving this, we get x minus 3 equal to 0 gives us x equal to 3. Solving the second equation, we get 2x equal to negative 1, which means x is going to be negative 1/2. So the zeros of the function are 3 and negative 1/2. So in other terms, the x-intercept of the polynomial or the function are 3, 0 and 1/2 negative, 0. So those are known as the zeros of the function, or the x-intercepts of the function, or the root of the function. The numbers are 3 and negative 1/2. And it's depending on whether you're describing as the x-intercept or not, you'll have to add the x and comma y to make it a point. So we could have done this problem using another method to find the 3 and the negative 1/2. We could have used the quadratic formula. The quadratic formula is just a shortcut so we can avoid doing all these middle steps. It's a formula that we can use to take us straight from the top line directly to the answer without having to go through the middle steps. The quadratic formula basically says if you have a polynomial of degree 2 of the form ax squared plus bx plus c, where a, b, and c are all numbers, then you can find x by using this formula, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So if you haven't memorized this formula, it's a good idea to pause here and try to commit this to memory. This is super useful and it will help us find solutions for polynomials of degree 2 very quickly, as long as a, b, c are all real numbers and a itself is not equal to 0, so that way we guarantee it's a second degree polynomial. So let's see if we can get the same numbers that we got before, the 3 and the negative 1/2, by using the quadratic formula. It's the same polynomial again, so I'm going to write the polynomial y equal to 2x squared minus 5x minus 3. And I'm going to pretend like I'm looking for the x-intercepts, or the zeros of the function. So I'm going to let y be equal to 0, which implies that the 2x squared minus 5x minus 3 has to be 0. Again, we're just replacing y with 0. That's why we're getting all this. And instead of using factoring this time, I'm going to look at my polynomial and decide what a, b, c are. So a is the leading term, the leading coefficient. B is the number in front of the x, so in this case it's going to be negative 5. And c is just the constant term at the very end. So c is going to be negative 3. And according to my quadratic formula, to get x, all I need to do is write negative b plus or minus square root of b squared minus 4ac, all divided by 2a. So keep in mind that b is negative 5, so we're going to replace all the b's with negative 5, keeping parentheses around everything. A is 2, so every time you see an a, you're going to replace it with 2. And finally, c is negative 3. Again, make sure you use parentheses so that you don't get anything wrong. Okay, so at this point, all we have to do is basically use PEMDAS. So let's begin with the double negative in front. That's going to be positive 5, plus or minus. Then we have negative 5 squared, which is going to be 25. And now we have to multiply the 4 times 2 times 3. So it doesn't matter what order you do it in. As long as you do all 3 of them, you'll be good to go. First, we need to notice that it's a positive value, because negative times negative will be positive, and 4 times 2 is 8. 8 times 3 will be 24. And on the denominator, we have 2 times 2, which is 4. So in other terms, this is saying we got to add 5 plus or minus the square root of 49, all divided by 4, which is the same thing as saying 5 plus or minus 7, because square root of 49 is 7, divided by 4. So we technically have two solutions, one that is a positive version of the answer, and one when we take the negative version. So in the positive case, we'll add 5 plus 7 and then divide everything by 4. So 5 plus 7 is going to be 12, and that's divided by 4. It's going to give us 3. And in the other case, we have to subtract 5 minus 7 over 4. That's going to be negative 2 over 4, which is the same thing as negative 1/2. And so these are the x values that we're looking for. So if I want to write it in the x-intercept form, the x-intercepts would be the numbers 3, 0, and negative 1/2, 0. If they're asking me for the roots or the zeros of the function, I could just stop when I get the value 3 and the value negative 1/2. And as you can see, the numbers are the same as before, right? It's the same problem, so we expect the same x-intercept in both cases, or the same zeros. Okay, so for example 4, we'll just repeat this whole process all over again. So it says find the roots or the zeros of the polynomial, and in this case the polynomial is written in terms of t. The polynomial is c of t equal to 2t cubed minus 18t. So I want the roots. So if I want the roots, that means I'm going to let the polynomial itself equal to 0. So in other terms, I'm going to grab the 2t cubed minus 18t and set it all equal to 0. So replace c of t with the 0. So c of t is 0, and that's it. Unfortunately, though, the polynomial here has degree 3, so I cannot use the quadratic formula. I have to stick with the factoring techniques that we know. So in this case, I've got 2t cubed minus 18t. And using my factoring knowledge, I can factor the GCF, which is 2t, because 2t cubed has a 2t factor, and 18t has a 2t factor as well. So when I take out the 2t, I'm left with t squared minus 9, because t squared times 2t will be the 2t cubed, and 9 times 2t will be the 18t that was already there. But t squared itself is t squared minus 9 itself is not completely factored. So let's keep going, and we can use the difference of squares there to write it as t minus 3 times t plus 3. And now my zero product property tells me if I have a product of two things, or in this case 3, doesn't matter which one, the zero product property says one of the factors must have been 0. Either the 2t had to be 0, or the t minus 3 had to be 0, or the t plus 3 had to be 0. For the product to be all equal to 0, one of the factors in the product must have been 0. Okay, for the first equation, we divide by 2 on both sides, and that's it. We're done. T is equal to 0 there, and we are finished with that first part of the problem. We can say that the first 0 of the polynomial is itself also 0. The second equation, I just add t to both sides, and I get t equal to 3, and that's the second 0 of the polynomial. So the 0 of the polynomial is the place where the polynomial crosses the x-axis, or in this case the t-axis, because we're using the variable t. And finally, for the third one, I just subtract 3 from both sides, and I get t equals to -3. And that's the end of the third one. So the place where this polynomial crosses the t-axis or the horizontal axis, well, there are actually 3 places: 0, 3, and -3. So the zeros of the polynomial are these 3 random numbers. Now, there are instances where the polynomial that's given to us is not easy to factor, or maybe it doesn't even factor at all, and we want to still find the roots, but without doing it by hand using the quadratic formula or the factoring techniques. So that's the purpose of this next problem. So what do you do if your polynomial cannot be factored easily or cannot be solved using the quadratic formula? Well, the calculator has a cool command that helps us find the roots of a polynomial. So let's begin by putting this polynomial x cubed plus 3x squared minus 2x minus 6 into the calculator. Okay, to do this, turn on your calculator, and once the calculator is on, you're going to click on the top left corner where it says y equal to, and just simply punch in the numbers that you see in your problem. So in this case, I'm seeing x to the power 3 first. So I'm going to click the x key, which is next to my alpha key. That gets an x on the screen, and I want to tell the calculator I want this to be raised to the power 3. So we put the little caret symbol and then 3 next to it. And we need to add the 3x squared next. Next, we'll subtract the 2x. And finally, subtract 6. So since I'm subtracting numbers, I use the big minus sign, not the little one next to the enter key, but I use the one above the plus sign key. So once you've typed in your polynomial into your calculator, we're going to click on graph, and you should see something like this on your screen. If you don't, click on zoom, then choose the standard zoom, which is zoom number 6, and the calculator will draw the polynomial, and it will show you something that looks like this. So we are interested in the places where this crosses the x-axis, and we can kind of see that the graph is crossing the horizontal axis in 3 different locations. We are interested in finding those locations. So what do we do next? We click second, and then we click the trace key, which is on the top row on our calculator. That opens up the calculate menu. We needed to click second first because calculate is in blue or yellow depending on your calculator type. In my case, it's blue. So I click the second key, then I click trace, and that gets me into this hidden menu where there's value, 0, minimum, maximum, and so on and so forth. I am looking for the zeros of the function, so I'm going to select option number 2 from this list. First thing I see here is the little butterfly blinking on my screen, so it's asking me for the left bound. So what that means is that I need to take my little butterfly and put it on the left side of the intersection that I'm looking for. So I'm going to be repeating this process 3 times, and so I'll begin with the far left intersection. So take your little butterfly, put it on the left side of the intersection. It seems like the intersection should be around -3, so I'm going to put it somewhere there and click enter. So that puts a little dotted line on my calculator screen, and now it's asking for the right bound. So all I have to do is just move a little bit away to the right of the intersection. So my intersection is somewhere around here, so I'm going to move away to the right of it and just click enter again. And now my calculator is going to want me to answer whether it needs to guess the answer or not. Obviously, that's what I wanted to do. I wanted to guess the solution, so I'm going to click enter. Now, the smaller the gap between the left and the right bounds is, the faster your calculator is going to return the solution, because it's not going to spend a ton of time looking for the answer. You're giving it fewer values to look through, basically. So we're going to click enter, and there we have it. It seems like the calculator have found the 0. It says that the 0 is at x equal to -3. Okay, it remains to find 2 more. So the next one seems to be somewhere around -1.5. So again, we're going to click second and then trace, and we're looking for the 0. So we're going to select the 0 command, or the 0 option. And again, it's going to want to know the left bound. So since my next intersection or my next crossing is happening around -1.5, I'm just going to take my little cursor and put it somewhere to the left of that. And next, I'm going to tell it to go to the right side of the intersection. And the gap here is bigger, so the calculator might take a smaller or maybe a little bit more time to find the solution. And so it's asking, should I guess? And yes, the answer is guess it for me. So click enter one more time. And the calculator returns -1.414214. Okay, so the last one seems like it should be somewhere around 1.5 as well. So we're going to click second, trace, and then I'm going to select option number 2 from this list of options, the 0. And again, I want to put it on the right side and the left side. So starting with the left first. So let's stop there. That's a good spot. And then I'm going to put it on the right side of the intersection with the x-axis, or on the right side of the 0. And so there you go. It seems like my bounded lines contain the intersection in the middle. And finally, click enter one more time to guess the solution. And I'm getting the same value, 1.1421. It's basically the same as the other one. The other one had a negative. This one has a positive. Okay, and so this is how you use your calculator to find the zeros of the function. You can use this grid that I provided for you here in order to graph your polynomial if you'd like. And the steps for doing what I just demonstrated on the calculator are written down underneath the problem. So in case you don't know how to do this, or in case you want to screenshot it, take a moment here to pause the video and screenshot this and keep it handy, because some of the problems will get complicated and it will be easier to find the zeros using the calculator. Okay, so next we'll talk about how to find the y-intercept, and this is significantly easier compared to the other problems that we've tackled. And by the way, what is the y-intercept? It's the place where the polynomial crosses the y-axis. So for example, in this particular problem, the y-intercept should be around -1, 2, 3, 4, around -5. So if I move my little butterfly, it's going to be basically somewhere around the place where it crosses the y-axis is somewhere around here. So as you can see, it's approximately around -5 on the, or -6 on the y-axis, somewhere around there. So how do you find it in general? How can you do this with or without a calculator? So if you have your calculator ready and you've already graphed it, no problem. you just click trace without clicking second or anything, and then just type 0 on your keyboard and then hit enter. And it will say, okay, -6. So 0 is the x-coordinate, the y-coordinate is -6. This is the place where the polynomial is crossing the y-axis. So what if you don't have a calculator, or what if you didn't bother graphing the polynomial? How do you find the y-intercept? So to find the y-intercept of any polynomial, you will let x be equal to 0. So in other terms, replace the x value in your problem with 0. So my problem contains 2x squared minus 5x minus 3. I'm going to erase the x's and replace them with x equal to 0. So every time I see an x, I remove it and write down 0. And this will give me y equal to 2 times 0 squared. That's just going to be 0. 5 times 0 is going to be 0. And -3. So my answer will be -3. And from all this, I can write that the y-intercept is the place where x is 0 and the y is -3. So the y-intercept as a point has two coordinates. The first one is always going to be 0 because it's the x value. And the second one is some number that you have to find, and it's typically easy to find it. You just plug in the 0 into the problem. So let's try it again one more time with p of x, which is x cubed plus 3x squared minus 2x minus 6. I'm looking for the y-intercept, so I'm going to let the x coordinate be equal to 0 in my problem. And my polynomial is the p of x polynomial. So every time I see an x, I'm going to remove it and write 0 there. So next we have the x cubed, but we don't write x, we write 0 cubed. Next we have the 3x squared. I don't write the x, I write 0 instead. And finally, -2x minus 6. Again, replace x with 0 and calculate. So as we can see that the polynomial in this case, when x is equal to 0, we get 0 plus 0 minus 0 minus 6. So the total is going to be -6. And so the y-intercept is 0, comma, -6. So again, nobody's going to remind you that to find the x-intercept and the y-intercept, you have to let some variable be equal to 0. You have to remember that yourself. In the case when you're looking for the y-intercept, you will make x equal to 0 and you will solve the problem. And that's what we did in this case. And earlier, when we were looking for the zeros of the function or the x-intercepts, we make the y be equal to 0. So an easy way to remember it, if you're looking for the x-intercept, make the opposite letter be 0. So if you're looking for x-intercept, make the y 0. If you're looking for the y-intercept, make x equal to 0. Okay, there are other types of functions that we will review in the next few pages, and let's begin with the absolute value function. Again, you want to be able to graph this with and without a calculator, so I'll show you how to do this with a calculator. The steps for finding the absolute value are listed over here in case you forget. But anyway, I want to graph y equal to the absolute value of x minus 3. If I'm doing this by hand, I can start by making a small table and pick some random values for x. For example, I don't know, 3 and 2 and 1 and maybe 4 and 5. And I plug the x values into my equation to see what ends up happening. So for example, when x is 1, the y will be the absolute value of 1 minus 3 plus 1, which is the absolute value of -2 plus 1. The absolute value of a negative number becomes positive, so I get 2 plus 1, which is going to be 3. So when x is 1, my y value is 3, then I can locate it on my grid, and then I move on to the next one. When x is equal to 2, the y is going to be 2 minus 3 in absolute values plus 1. This is -1 absolute value plus 1, which is 1 plus 1, which is going to be 2. So when x is 2, the y is also 2. And I continue the same way to find the other values. So when when x is equal to 3, the y is going to be 3 minus 3 and plus 1. So basically that's 0 plus 1, which is going to give me just simply 1. So when x is 3, the y is going to be 1. When x is 4, the y is going to be 4 minus 3 in absolute values plus 1, and that's going to give me 1 in absolute values plus 1, which is going to be 2. So 4 on the x value gives me 2 on the y value. And as we can see, It's starting to look like a low V shape, and that's the expected shape that we should have when we're graphing an absolute value function. So let's finish it up. When x is 5, the y is going to be the absolute value of 5 minus 3 plus 1. The absolute value of 5 minus 3 is going to be the absolute value of 2, which is exactly 2, and 2 plus 1 is going to be 3. So x5 gives me 3 again. So you can see that the points line up in a V shape, and that's the expected shape when you're graphing an absolute value function. And so earlier, when I decided the values of my problem, I started with the 3 first, and then I picked 1 and 2, then 4 and 5. Why did I decide on 3 right away? Because I saw that I have x minus 3 in my equation inside absolute value. So I was thinking to myself, what number would make that 0? So that's typically the tip of the absolute value, the place where the absolute value turns around. So in this case, it was easy to guess the number was 3. Then I picked 2 numbers before and 2 numbers after just to find the shapes of the lines before and after. You can get away by choosing 3, 2, and 4 only, but it's always good to have more points just to make sure that everything is lining up correctly. That's why I chose 2 numbers before the 3 and 2 numbers after the 3. That way I don't make any mistakes when I'm graphing my lines. Okay, so let's see how this could be done with our TI calculator next. Okay, so here's the calculator again. In this case, I'm still seeing the polynomial that we did in the previous problem. So I'm going to click on the y, and then I'm just going to click clear to remove all the previous entries for the previous polynomial. Next, what I'll do is I'll click on math. And once I click on math, I'm going to move over to the numbers column. And the very first option says ABS, which stands for absolute value. So I'm going to click 1. And for my calculator, it shows me the actual absolute value lines. All I have to do is pick x minus 3 inside of it, and then put a plus 1 on the outside. If you have one of the older TI generation calculators, you might have something slightly different, so I'll show you what that looks like for you. So if you have an older TI calculator, the steps are going to be the same. So first clear the Y1, and then you're going to click on math, then move over once to the right to the numbers column, then click the absolute value key, which is the very first one, and type in your x minus 3. Now you have to remember to close the absolute value. So how do we do that here? We just add the extra parentheses. So the older TI calculators didn't have the math print, the pretty fonts that will put the lines. So that's the way they handled that. And then we'll click plus 1. And now we are ready. We're done. We just entered the whole polynomial. So we click on graph, and there you have it. So this is the same graph that we produced by hand. As a matter of fact, if you like, you can trace some numbers. So if I trace the value 3, I will see that it's given me 3 on the x-axis and 1 on the y-axis. So this is the same value found in our table. If I click trace 1, it'll show me 1 and 3. So the x is 1, the y is 3. And if I do 2, I'll see 2, 2. These are the same values that we found in our table previously when we did this process by hand. So again, it's up to you. You can use the TI calculator, or you can use your tabular method, which is the one that I did at the beginning, to get the graph done. Either way, you should end up with the same sort of general look. And that ends our short discussion of absolute value functions. So let's talk about rational functions next. So we've come across a couple of these in the previous sections, but a rational function is basically a type of function where you have a numerator and a denominator, both made up of polynomials. So the key special thing here is that the denominator should have some letters in it, or some variables. Now, obviously, these functions are defined as long as the denominator is not equal to 0. So if a number makes the denominator 0, that's bad, then the whole thing just fails to exist, and we end up with all kinds of problems. And so let's look at example number 8, which says, consider the function f of x, which is equal to f of x equal to x plus 1 over x minus 2. First of all, what's the domain of the function? So what numbers am I allowed to legally plug into this f of x without blowing the whole thing up and ending up with no solutions and so on and so forth? So the key here is to look at the denominator. and ask yourself, can the denominator accept every number, every real number? If the answer is no, then your domain is going to have restriction. But if your domain can accept any value, then life is good. And unfortunately, the domain will have to be restricted for this function f of x. So we will note that x minus 2 is going to be 0 when x itself is equal to 2. And this turns out to be kind of a bad number, right? So it is bad if x turns out to be 2, because then I'll have 2 plus 1 on the numerator divided by 2 minus 1 on, 2 minus 2 on the denominator, and that will be 3 divided by 0, and unfortunately we cannot divide by 0. The function becomes undefined, it won't even exist. So the domain is going to be all the real numbers except for 2. So on the x-axis, basically, I can choose any number that I like except the number 2. So any number is legal except for 2 itself. 2 is forbidden, it's not allowed, but everything else is perfectly good. So how do I say that? We have two different ways. We can either use the set notation or the interval notation. So I'll start with the set builder notation. The domain is every x as long as I don't pick the number 2, which is the bad number. So this is the set builder notation. Or if I want the interval notation, I would write negative infinity, comma 2, with negative infinity having parentheses, and the 2 also gets parentheses. Remember, the parentheses means don't take this number, don't include the 2. And infinity is not a number, so we can't even include it, so that's why we always put parentheses there. And we can take every other number after 2. So again, from 2 to infinity, all those numbers are legal, but not infinity itself and not 2 itself. So that's why, again, we use parentheses. So that is the domain of the function written in interval notation. This is the domain of the function written in set builder notation. So the domain includes all the legal values for which the function will return something useful. It will not become undefined. Okay, so the next part, it says, does this function have any zeros? So the function f of x, which is x plus 1 divided by x plus 2, does it have any zeros? So remember, the zeros are basically the values for which the y becomes equal to 0. So we're going to let y be equal to 0. Technically, the y is this, f of x, so this is going to become 0. So we need to solve the problem that says 0 equals x plus 1 divided by x plus 2. And so how do you solve this? There are many different ways of doing it, but you can imagine there's a 1 invisible under the 0. 0 divided by anything is going to be 0. And you could just cross multiply. That's one option. The other option is just to remember that for a fraction to be equal to 0, it means that the numerator has to be equal to 0. So the numerator is x plus 1, and so it needs to be 0 itself for the whole rational expression to be 0. And when does this happen? This happens when x is equal to negative 1. So this is known as the 0 of the function. We can also say that the x-intercept is the place where x is equal to negative 1 and y is equal to 0. Okay, so next it's asking us for the y-intercept. So remember, the function f of x is the function x plus 1 divided by x plus 2. And we want to find the y-intercept. So what do? I'm going to grab this function and I'm going to let x be equal to 0. So everywhere I see an x value, I'm going to make it 0. So there's 0 there, there's 0 there, and finally there's 0 here. So 0 plus 1 is going to be 1, and 0 plus 2 is going to be 2. And that's it. So simple, straightforward. And I'm going to record that the y-intercept is actually 0 for the x, 1/2 for the y. So notice how the y-intercept always has 0 on the x value, and the x-intercept always has 0 on the y value. So this is kind of key. This is what we're trying to get out of this whole discussion. Okay, lastly, we want to graph this function f of x, and graphing this by hand is going to be very difficult. So again, we'll use the TI calculator to get the graph. So let's go and do that. So on my calculator screen, I still see the absolute value function that we graphed in the previous example. So let's get rid of it. We're going to click on the y, and we're going to clear the first line. I'm going to put my f of x, which is x plus 1 divided by x minus 2, over on y1. So because my function has a numerator and a denominator, I need to put everything inside parentheses. So I'm going to start with the parentheses x plus 1 for the numerator, divided by the parentheses, and then x minus 2 for the denominator. So basically, taking the original problem that you have, you will need to translate it into the format x plus 1 divided by x minus 2 and put it this way into your calculator. Otherwise, your calculator is not going to understand what's going on, unless if you have one of those newer version with the math print where it shows you the fraction bar and everything else, in which case it's a little bit more forgiving. But the older TI calculators, they need this particular format in order to get the graph done quickly and efficiently and correctly. Okay, so once you've typed everything in, click on zoom, then click 6 to reset the window in case you changed it before, and that's what the graph looks like. So the interesting thing here that we're not seeing on the TI calculator screen is that there's some invisible lines that the graph will tend to get closer and closer to. So I'll do this by hand real quick to show you what I'm talking about. So first of all, we discovered that the x equal to 2 was a forbidden bad value. So that means there's some kind of like line over here where x is equal to 2. Let me make this thicker. There's some kind of line where x is equal to 2 that we're not allowed to cross. That was a forbidden bad value, so that was not in our domain. So this is one of the imaginary lines that we're not going to be able to cross. And we will discover later on the semester that there's another line, which is the y equal to, in this case, it's going to be 1 for this problem, which is another line. It's a horizontal line that we're not allowed to cross, basically. So your graph, when it's done, is going to be hugging those lines. And from the view on my calculator screen, it seems like I should be having something like this. So keep in mind the x and y intercept. So when you make your graph, make sure you're crossing the point 0, negative 1/2. So, I'm kind of roughly putting around there. And the other point that we found was negative 1, comma 0. So the graph crosses these 2 points at the x and the y intercept, and everywhere else it's not touching any axis, and it's not going to touch those dotted imaginary lines that usually we don't draw, but for now I'm going to keep them both in here because they're going to be the guidelines for our graph, basically. So in the future, we will be graphing this particular function and similar ones the long way by using limits and maximas and minimas and inflection points, all these things that you haven't talked about yet in this semester or in this course. But this is a good practice so that we can see what the process is going to look like eventually with extra more details everywhere. Okay, now let's turn our attention to radical or root functions. Oftentimes in this class, we will need to convert from root notation to power and vice versa. And the formula we will use to do that is right here in the middle of the page. This formula says if you have b to the fraction power m over n, then that could be written in a couple of different ways as the nth root of b to the m or the nth root of b all to the power of m. So in other terms, if I have something like 3 to the power of 1/2, I can write that as the square root with the 2 there and 3 to the power of 1, or the square root of 3 all raised to the power of 1. Obviously, when the powers are 1 and 2, we typically don't write them down, and so we end up with the same kind of notation at the end. This is just the square root of 3. So again, this is going to be a very quick review of radical functions, and so we'll begin with the function f of x equal to the square root of 9 minus x squared, or in other terms, 9 minus x squared to the power of 1/2. So part 1 of this question is asking us to rewrite it in the form of a root, and so like I mentioned earlier, we will use the formula. So 9 minus x squared with the power of 1/2, that's the same thing as the square root of 9 minus x squared. The 9 minus x squared is typically called the radicand, and the square root will have the power 2, and it's all raised to the power of 1, or simply the square root of 9 minus x squared to the power of 1. And as I said before, you don't typically have to write the power 1 and the power 2 on the radical. So The quick version of this would just simply say the square root of 9 minus x squared. So that is the way we rewrite this function to show that it contains a radical notation, or a square root in this case. When you have an even power, it's important to pay attention to the domain. And so the next question is basically asking us to figure out the domain of the function f of x, which is the square root of 9 minus x squared. And what we have to pay attention to in this case is that the radicand cannot be negative. It can be 0. 9 minus x squared could add up to 0, in which case the square root of 0 will be simply 0. But I can't have a negative inside, right? This would not be a real number, and so we're not interested in that in this particular course. So the domain requires me to say that I need to have the 9 minus x squared be greater than or equal to 0. So it needs to be positive, or it could be exactly equal to 0. Now, to solve this type of inequality, you'll need some algebra skills, but first I'm going to start by rewriting the inequality. I'm going to factor the 9 minus x squared, and I'm going to rewrite it as 3 minus x times 3 plus x. So I need it still to be greater than or equal to 0. So first of all, to solve this type of problem, I need to find the roots of the polynomial 3 minus x times 3 plus x. So the roots in this case, I hope you can clearly see that they are 3 and -3. These are the numbers that would make each of these parentheses equal to 0. This one here would be equal to 0 if I plug in x equal to 3, and this one here would be equal to 0 if I plug in -3. Now, we are not done yet. What we have to do next is do some testing to figure out what part of the real numbers we can take. So what I'll do is I'll draw the real number line. So this represents all the numbers in the world. And I'll label it with negative infinity on one side, positive infinity on the other side, and the numbers that I'm interested in are just -3 and +3. As you can see, this splits the number line into 3 different sections, one, the middle one here, and the third one there. So there's 3 sections, and some of them will be the correct domain, some of them will not be inside the domain. So to figure out which section to take, what we'll do is just do some random testing with some random numbers. So what we'll do is we'll pick a number between negative infinity and -3. So for example, you can pick -5, you can pick -10, you can pick whatever you want between negative infinity and -3, and plug that into the function to see if it ends up being a real number or an imaginary solution, in which case we will not count it. And we'll repeat the same process again. So we'll test a number between -3 and 3. I'm going to pick 0 there. And then finally, we'll pick another number between 3 and infinity. So I'm going to pick, I don't know, 10 again. So let's start with the middle one, because I think that's the easiest one. If I put 0 into this function where x is, I'm going to end up with 9 minus 0 squared, which is the same thing as the square root of 9, which will be 3. And so this is a +3. It's a real number. And I can now confirm that the middle section will be inside the domain, right? It's giving me numbers that are real at the end. So great. So now let's do the testing on the other 2 intervals. Okay, so if I try to do the same test on 10, if I plug 10 into the original function, what will happen is I'll end up with 9 minus 10 squared. This will be 9 minus 100, and that's going to be the square root of some random number, in this case 91. Who cares about the actual number? Just the fact that there's a minus inside, that tells me that this is not a real answer. It's going to be an imaginary solution. So that tells me that I should not take the third interval. That's not part of the domain, because if I plug a number from there into the original function, I'm ending up with something imaginary. And finally, we'll do the test on the -10 that we chose from the first interval. So I'm going to take -10 from the first interval and plug it into the function. So I'm going to end up with 9 minus -10, everybody squared. So that's going to be 9 minus 100 again, because -10 squared will be 100, and the minus in the middle has to come down. That's the same as the previous one. It's the square root of -91, which again is not a real number. It's an imaginary number. So that means, again, do not take that first interval. So the only interval that we're allowed to choose in this case is the middle interval, and that represents the domain of our function. So in this case, I'm going to write -3, 3. Those are the beginning and end of the interval. And remember, in this problem, I'm allowed to let the inequality be equal to 0. Therefore, the 3 and -3 will have kind of brackets on them, meaning they can be included in my domain. So really think about it. If you put 3 into this function, you're going to have square root of 9 minus 9, which is 0. And so it's okay. It's a real answer. And the same thing happens with -3. So this is the domain written in interval notation. But if I want to write it in set builder notation, then it would look like something like this. Take any x as long as that x is between -3 and +3. Okay, so for part 3, it's asking us if this function has any y-intercepts or any x-intercepts. So this is the same as before. To answer this question, we'll have to make either the x be 0 or the y be 0 and figure out what the answer is. So let me begin with the easy one, which is the y-intercept. So to find the y-intercept, I'm just going to let the x be equal to 0. So in this case, to find the y-intercept, let x be equal to 0, and the 0 is part of the domain. It's a number between -3 and 3, so it's legit. We can answer this question. So if I let x equal to 0, then the f of x will be f of 0 equal to, instead of 9 minus x squared, I'm going to write 9 minus 0 squared. And that's going to be the square root of 9 minus 0, which is the square root of 9, which is really simply just 3. So there is a y-intercept, and the point that represents the y-intercept has the coordinates 0 for the x, 3 for the y. Okay, next let's look for the x-intercepts. So to find the x-intercepts, I'm going to let the y be equal to 0, so it's always the opposite letter. And the y is just simply the f of x. So I want the 0 to be equal to the square root of 9 minus x squared. So that means what? That means first I need to solve this, so I need to get rid of the square root. To get rid of the square root, I could just square both sides of this equation. And so when I square both sides of the equation, 0 squared is still going to be 0, and 9 minus x squared inside the square root gets squared. We just end up with 9 minus x squared. And we already know that the numbers that will make this equation equal to 0 are 3 and -3. So there are 2 points in this case that represent the x-intercepts. The first one is 3, 0, and the second one is going to be -3, 0. So there are 3 solutions in this particular problem: 0, 3, and 3, 0, -3, 0. The last thing I'll do is sketch a graph of this function, and again, I'm going to use my TI calculator to do this, and I have a graph here for you, or a grid here for you, where you can plot it on your own if you want to copy it to the paper. But let's see what it looks like when you graph this function on your TI calculator. So just like before, you're going to turn on your calculator, you're going to click the Y key, which is on the top left side, and you're going to put the square root of 9 minus x squared. So I'm using the square root, which is the same key as the x squared key, but you have to click second first to access it because it's in blue. Sometimes it's in yellow, depending on your calculator model. But for the older TI calculators, this is what it would look like. You'll have to type 9 and then the big minus sign, then the letter x or the variable x, then click the square key, and finally you'll have to close the parentheses. If you have one of the newer calculators with the pretty math print turned on, then it will show you a square root, and then you can type everything inside, and you don't need to use parentheses, but this is how it looks for the majority of the TI calculators. Once you're done, you can just click graph, and you'll see that it looks like an arc. Now, this is supposed to be a circle, or at least half a circle, that basically starts off at -3 and ends at +3 there, and passes through the point 3 there. So it's technically supposed to be like half a circle, but the calculator does not have the power to show this. It's showing us kind of a weird graph. It's showing us only a portion of the circle, and this is just this is an issue with the TI calculator and how it plots the points and then graphs them. So what I'll do to make the circle connect to the x-axis on both sides, I'll have to go ahead and modify my Windows settings a little bit. So instead of starting from -10, I'll start off from -4. And instead of stopping at 10 on the x-max, I'll stop it at 4. So in this case, I'm using the tiny little minus sign 4 and then the big 4 next. And so if I click graph, you'll see that the graph starts to really try to reach the x-axis again. Let's keep modifying. So go back to window and let's go ahead and change the y minimum, y maximums. So on the y minimum, I really don't need to see a lot of negative y values. So I'm just going to start at -1. And I know that the height of the circle is around 3. So I'll just go up to y maximum equal to 4. And so if I do that, let's see what the graph looks like. Again, you can see it's trying to touch the x-axis at -3 and 3, but it's not able to. So to make it try to connect, let's go back to window again. And this time what I'll do is I'll go down a little bit to where it says delta x and trace step and all that. I'm going to make this smaller. So it says 0.03 for me right now. I'm going to make it 0.01, for example. And let me click graph and see what happens now. So you can see it's showing me that part of the graph, and it's really, really close to the x-axis. And that's what I wanted to see, basically. I want to show you that the calculator is not always great at graphing these things. This is why we're going to use methods besides the calculator to graph these functions, because the calculator is not always the most reliable tool. And so that's a perfect example of that and why you need to continue learning more and more advanced techniques in calculus. So in the future, we will use methods like the first derivative and the second derivative, inflection points, maximas and minimas to get these graphs. But for now, it's asking me just for a simple sketch of the curve. And sketch just means it doesn't have to be perfect. It just needs to look like the correct graph. In this case, just the upper half of a circle, starting from -3, 0 on the x-axis, ending at 3, 0 on the x-axis, and passing through the point 0, 3, which is the y-intercept. Those are all the points that we found previously in the earlier parts of this question, and so that's how they're displayed. Okay, the last thing we're going to talk about in this section is the piecewise defined functions. And so what's a piecewise defined function? It's a function in which more than one formula is used to define the output. So something like this is a piecewise defined function. So sometimes they will have one formula and a second one and a third one. Sometimes there's only two formulas, and it could be many, many more. It could be 10 formulas there, and usually they will list the domain. So what numbers are you allowed to plug into this formula, and so on and so forth. So an example of one of these piecewise defined functions is found here. The CG has two formulas. The first one is the 25, and the second one, it says 25 plus 10 times g minus 2. So if I want to plug any number between 0 and 2, I'm supposed to use the first equation. But if I need to plug a number between 2 and infinity, so something greater than or equal to 2, then I'm supposed to use the second formula to calculate the output to see what the output of the function is going to be. And so in this case, we're told that a cell phone company uses the function below to determine the cost in dollars for using G gigabytes of data transfer. So if you use something like 1 gigabytes, then you're supposed to pay a flat fee of $25. If you use 1.5 gigabytes, again, you pay the flat fee. But if you go over the 2 gigs limit, then your bill is calculated using the formula that's written here, 25 plus 10 times G minus 2. So my question is to find the cost using 1.5 gigabytes and then to do the same thing again with 4 gigabytes. So there are two questions really to solve. First, C of 1.5. And so since 1.5, the number that I'm given, is between 0 and 2, then the formula I'm supposed to use is the first formula. So the first formula basically doesn't have anything. It just says use always 25. So I'll have to pay $25 if I use 1.5 gigs of data in my cell phone plan. Okay, so that's because the number that I'm inputting is a number between 0 and 2. Now, if I decide to go over the limit of 2, and I want to know how much it will cost me to use 4 gigs of data, then now the formula changes. It's going to be 25 plus 10 times the g. In this case, the g is going to be 4. This is just a random number that we're testing, and then minus 2. So in this case, I have to use the second equation to determine the cost that I will have. So this is going to be 25 plus 10 times 2. So in other terms, 25 plus 20, which means I have to pay $45. So if I go over the limit of 2, then I will have to pay extra money, $45, because the second formula is used. And that's because, again, the number that is being placed, or the input, is bigger than or equal to 2, which is that domain right there. Okay, so that was a quick, simple example. What we're going to do next is complicate things a little bit and see how the graph can be produced. So in example 11, we're given a function again with two formulas, x plus 3 if x is less than negative 3, and 2x minus 1 if x is greater than or equal to negative 3. And I'm being asked to find a few different values, f of 2, f0, and so on. So let's begin with the first one, f2. So how can I find f of 2? The first thing I'm going to ask myself is the 2 and how it relates to these domains. Is it smaller than negative 3, or is it bigger than or equal to negative 3? And obviously, 2 is bigger than or equal to negative 3. So the formula that I'm supposed to use for this part of the problem is the formula 2x minus 1. So 2 times x minus 1, but keep in mind that the x that you're plugging in is the number 2. And so 2 times 2 is going to be 4 minus 1. The total is going to be 3, and that's it. So the point I get is the point 2 for the x, 3 for the y. Okay, let's do it again. When I plug in 0, so what's going to happen? How does 0 relate to the domains? Is it smaller than negative 3, or is it bigger than or equal to negative 3? And obviously, 0 is bigger than or equal to negative 3. So again, the formula is the same as before. 2 times x minus 1, where x is 0. So again, use the same formula. And so what do I get here? I get 0 minus 1, which is negative 1. So the output is negative 1 when the input is 0. Okay, keep going. Next, we have f of negative 2. So again, you should be asking, how does negative 2 relate to the domains? Is it smaller than negative 3, or is it bigger than negative 3? And I hope you can tell that it's bigger than negative 3. So we use the same formula as before, 2 times x minus 1. It's the same blue formula, but this time x is negative 2. And the total will be negative 4 minus 1, which is negative 5, giving us the point negative 2 comma negative 5. Okay, we're doing this because in the next part of the question, we will be graphing this function. So we'll need a few points. So instead of making a table here, I'm just writing it the old-fashioned way. All right, so next we have f of negative 3. So in this case, the value I'm plugging in is negative 3. And how does negative 3 relate to my domains? Is it strictly smaller than negative 3, or is it bigger than or equal to negative 3? And I think you can tell that it should be bigger than or equal to negative 3. And so, as before, this is the fourth time we're using the same formula. I'm supposed to use the blue formula and plug in negative 3 into the x. So that's going to be negative 6 minus 1, which is negative 7. And so when the input is negative 3, the output is going to be negative 7. Okay, so next let's look at f of negative 4. So how to find f of negative 4? So again, the number here is negative 4. And how does that compare to these values in my domain? Is it smaller than negative 3 or bigger than or equal to negative 3? And the answer is that negative 4 is smaller than negative 3. So this time I will have to use the first formula, which is x plus 3. So x first plus 3. The x is going to go here. And the x in this case will be just simply negative 4. And so negative 4 plus 3 is going to be a total of negative 1. And the point I'm getting has input negative 4 and output negative 1. So this is the ordered pair that I'm supposed to use there. Finally, f of negative 5. And as before, how does the negative 5 compare to the domains? I can tell that negative 5 is smaller than negative 3. So I'm going to use the same formula before. So negative 5 plus 3 is the answer. And so that's going to be negative 2 total. And so my point is going to have input negative 5 and output negative 2. So that's the first part of the problem, and it's finished. And now let's try to graph this function. And what we're going to do is graph it by hand since I have all this information already in front of me. So the first thing I'm going to do is go down here and draw a dashed line at -3, because that's the border, right? I like to call it the border because it's the number that separates my domains. It's -3 and -3 again. So I'm going to put like an imaginary line right here, and let me do it with this thing. So this is the imaginary border. I'm going to erase that border later on, but for now, let's keep it so that we know that we have one graph before it and a different graph after it. And to finish the problem off, I'm going to use these points as my guides and also these points as my guide. So first of all, I have a point 2, 3. The point 2, 3 will be the point right here. Next, the point is 0, -1. When x is 0, the y is -1. That point is right there. Next, I have the point -2, -5. When x is -2, the y is -5. I get this point over here. And we're starting to see that they line up in a straight line. And finally, the point is -3, -7. That's right on the border, and that's going to be a solid point for now. So this is the first part of the graph, and let me make it a solid red line. So there it is. That's how the graph looks like on one side of the border. And now, what about the other side? So here we go. The second coordinates we have are -4, -1. When x is 4, the y is -1. That's this point right there. And finally, the point is -5, -2. When x is -5, the y is -2. And that gives me this point over here. So again, I can kind of see that they line up in a straight line. And this time I'm going to make it blue. And I'm going to extend it all the way to the border. But when I touch the border, I'm not going to have a solid point there. I'm going to actually put a round circle here to remind the person reading this that I cannot touch the border. So the line extends all the way to the border, but it doesn't actually touch the border. Whereas on the other side, it's actually touching the border. So that's why we made the solid circle on the other side, but we didn't do it on the left. And at the end, when you're finished, you can erase that line. And that's it. That's the final graph. Okay, so now you might be wondering, can I do this with the TI calculator? Can I graph this function with the TI calculator? And the answer is yes, you can. It's a little bit difficult to plug it in, to put all the numbers in, but let me show you how you're going to punch these numbers in. So first of all, my function f of x is a piecewise function. So for the calculator, the way you set it up or the way you enter it is kind of funky. So first, what you're going to do is put the first equation, and the domain gets multiplied by the first equation, sort of. Then you put the second equation and you multiply it with the domain of that second equation. So in my case, the f of x that I type into my calculator will look something like this. First, x plus 3 is my first equation, and the condition or the domain is x is supposed to be less than -3. And then I'm going to have to put a plus sign and type in the second equation, which was 2x minus 1, along with the corresponding domain for that equation, which is x bigger than -3. So for me, basically, the yellow equation will be first along with its domain, and the blue equation will be second along with its domain. So let's see how you can type all this into the calculator. I'll show you the steps next. So here we go. Go to the Y again to enter this menu where you plug the equations in. And I'm going to have to use some parentheses. And some calculators are not able to do this. Maybe your calculator is able to do it, maybe not, but it's worth a shot to see if it works. So first type in x plus 3. This is pretty normal. Close the parentheses. Now we need to put the domain. The domain is x less than -3. So I'm going to type x first. Then I need to enter this test menu. It's in blue for me, it may be in yellow for you, but it's the same key as the math key. So we're going to click second and then click the math key. That opens up some menu with the symbols less than, greater than, and so on. So I want the less than symbol first. This is option number 5 for me, so you can either click 5 on your keyboard or just go down or up with your arrow keys until you find it. So click enter, then close the rest of the command with -3, and then close the parentheses. So that's my first equation along with its domain. Then I got to tell the calculator there's a second equation. The way I do that is I put a plus sign, then I put in the parentheses again, and I write the second equation, which is 2x the big minus sign, and then 1, close the parentheses, and I got to give it the domain of that equation. So I'm going to open another set of parentheses and then type again x, and I need a greater than or equal to symbol. So again, the way you do it is you click second, and then you click the math key, and find greater than or equal to in this list. It's option number 4 for me. I'm going to select it, and then type the -3, and finally close the parentheses. So if everything is good on your calculator, you should be able to see the same graph that we produced by hand. Let's click on zoom and pick the standard zoom so that we are always starting with the standard numbers. And there we go. So that's what the graph looks like. And if you try to trace some of the random numbers we plugged in earlier, we had 0, for example, gives us -1. When x was -2, we got -5. When x was -3, notice what the calculator is going to do. It's going to go straight to the solid point. So on the other side, it looks like when x is -3, the y should be approximately 0, and that's the open circle like we did in our side, right? We put an open circle there in that region because we're not technically allowed to touch the border on that side, but we're allowed to touch it on the red side of the curve. Okay, so let's give this example number 12 another shot. So this is sort of similar. This time, though, we have 1, 2, 3 formulas along with 3 different domains corresponding to each formula. So we will have to find a bunch of numbers starting with g of 2. So g of 2, I'm not going to use a lot of colors this time. So 2, I'm thinking 2 is bigger than or equal to 1, and my equation is just x. So whatever number I get, the output is identical. So when the input is 2, the output is also 2. So that's it. So next, let's try g of 1. So g of 1, when x is equal to 1, the number 1 is bigger than or equal to 1. So again, use the same formula as before. And the formula is just x. So whatever your input is, your output is going to match the input. So again, we get 1, 1. So the points so far are 2 for the x, 2 for the y, 1 for the x, 1 for the y. Okay, let's look at g of 0 next. So g of 0. So where does 0 live? Is it bigger than 1? Nope, it's not. Is it less than -2? Nope, it's not. So it's between -2 and 1. And so the output is going to be 2 no matter what. So no matter what x I plug in, as long as the x is between -2 and 1, I get always the same output, which is 2. So 0 gives me 2 back. Okay, so let's try g of -1. G of -1. So again, the number -1 is between -2 and 1. So the output is always the same there. The output is always 2. And so the point that I get is -1, 2. Okay, so what's next? Next we have g of -2. So when x is -2, which equation should I use? When x is equal to -2, the equation satisfies this first inequality. So therefore, my output is always -3. So when the input is -2, the output is going to be -3. And finally, the last point that we have to plug in is g of -3. So g of -3, the number -3 is a number that is smaller than or equal to -2. So the output is always the same. G of -3 will be -3 as well. So the point is going to be -3, -3. Okay, so once I've done this, they want me to graph the function. So first of all, let's draw some borders. So where are the borders going to be? There's a border at -2 because that's one of the numbers I see there in my domain. So let me draw the border. So this is one of them. Let me use the straight line command. So there we go. That's the first line. That's the border. And the other number that I see in my border is 1. It's shown up a couple times. So the 1 is going to be another border. So when x is equal to 1, so that's the other border. So eventually I'm going to erase these borders once I finish graphing everything. So now let's use our points. The point is 2, 2. When x is 2, the y is also 2. So that's 1 point there. Next, we have the point 1, 1. So 1, 1, that's right on the border. So great. It looks like these are going to give me a straight line that looks this way. The next one is 0, 2. When x is 0, the y is 2. And next we have the point -1, 2. When x is -1, the y is 2. So that's that point right there. So between the borders, it looks like I have a straight horizontal line, kind of. And so let's see what's going on the other side. -2 gives me -3. When x is -2, the y gives me -3. So that's this point right here, right at the border. And finally, the last point we have is -3, -3. That's this point over here. So let's finish drawing. So let me make my line solid first, and let me start with a blue line for this side over here. So this is the graph on the far right. So my graph points up and it touches the border, so that point is going to be solid for sure. So the point 1, 1 is going to be a solid point. It's right at the border. And next, let's draw the middle line. I'm going to use red this time. So it's a horizontal line that stretches from one border to the other, passing through those points. However, the line is not able to touch the points. The line is not able to touch the border. So to say that, I put empty circle and another empty circle. You can't have two solid circles, by the way. That's how I know that the line cannot be touching the borders. There's already a solid circle here, and there's already a solid circle here. So that's how I know that these other points at the border have to be empty. And finally, let's draw the third line. This time I'm going to use orange for that. And the line looks like this. And again, it is touching the border, and that's it. We are now finished. Let's get rid of these borders, and that's the final graph. So we have a solid point at -2, -3. This is another solid point. And with that, we're basically finished with this example. Now, unfortunately, if you try to do the same procedure we did for the previous problem here and try to graph this function with the 3 different formulas into the calculator, you'll see that the graph is completely wrong. This is not the graph that we're supposed to have, and I don't know why the calculator is able to graph functions with 2 formulas, but it can't do 3. So this is again why we need to rely on the methods by hand to graph these functions and rather not on the calculator. Okay, so the last thing that remains is to be able to write the name of the function given the graph of the function. So we are presented with a graph in example 13, and they want us to write the function's name. So I'm going to start by calling the function f of x. You can call it g of x or t of x or whatever you want. I'm seeing 3 different lines in this graph, so there's going to be 3 different formulas, 1, 2, and 3, and each one of them is going to have a different condition. So I'm going to add ifs so that we can figure out the conditions. So the first graph on the far left ends at the point where x would be a -2. So I know that this is going to be true if x is less than -2. I know it's going to be less than, not less than or equal to, because the point there is an open point. So the first graph of this line does not include the point at the border, and the border, remember, is the point -2, or on the x-axis. Now, what is the equation that represents this line? This line is horizontal. It's always the same value, and the value is -3. I can see that on the y-axis. So the formula there will be just simply -3. So the function will be always -3 when x is less than -2, and it does not include the point at the border. And again, that's because the point is open. So this is what we call an open point because it's hollow. Okay, so the next one, the easiest one, is this guy right here, the far right graph. And so again, where is the border there? The graph changes when I hit the point x equal to 2. It seems like the graph changes from being a slanted line to be a horizontal line. And again, the point here is hollow or open. So this is an open point. That means that the graph does not include that point. So this is true when x is bigger than 2. So when x is bigger than 2, what is the formula I'm getting? Well, it seems like the line is always at the same height. It's not changing. It's always the same height, and that height is just simply 4. So the formula is 4. The output is always the same, 4, when the number that I plug in is a random number that is bigger than 2, not including 2 itself. Okay, so the final section that we have to worry about is the one in the middle, and I can see that the borders there are 2 and -2 on the x-axis, and the points on this end and this end are closed points. So closed because they are basically solid, right? So hollow or open, closed, or solid. So the points are closed, so that means from -2 to +2, I'm going to have some kind of a number as the output, and we need to figure out what formula gives us that output. But notice how I'm putting an equal sign because the points are closed. So because the points are closed, I'm putting equals on my inequality. And when the points are open, I'm putting just less than or greater than without the equal sign. Now, okay, what's the formula for the middle line? So let's test it out a little bit. When x is -2, I'm getting the same y-coordinate -2. When x is -1, I get the same y-coordinate on the line. The point is also going to have a y-coordinate -1. When x is 0 on the origin, the y is also 0. Okay, when x is 1, I get the point here, which also has y-coordinate, which is also 1. And finally, when x is 2, the y-coordinate is also going to be 2. So no matter what the input is, the output is always the same. So that means the equation that gives me that is just simply x. And so this is basically it. This is the name of the function in this particular problem. Now in the future, we're going to have a lot more complicated functions, but this is how we're going to approach them. Figure out the borders, the places where an inequality ends or another one starts, and then figure out the formula to generate the line or the circle or the parabola that you have on the actual graph. And so that's the end of the section. So thank you for watching.